who speaks on bracketed ternary additive problems. Yeah.
Thank you, Mel. Good morning, New York. Good afternoon, Europe. Bracketed ternary additive problems are derivatives of the classical ternary additive problems of Waring's type. So before we enter the bracketed story, let me start with briefly recalling what the classical ternary additive problems are. Everybody knows Waring's problem. The famous circle method is just over 100 years old. It solves Waring's problem. It gives us asymptotic formulas for the number of representations of an integer as the sum of cave powers and so on. It adopts easily to sums of unlike powers, but we shouldn't take things too easily. If we only have two summons, so the famous binary additive problems, then I will never end up with a result of Waring's type saying that when n is large, I can write it as a cave power and an elf power, unless I'm doing something very trivial, k and l are 1. Things are better with three summons. Now with a, b, and c, the exponents I want, and to avoid trivialities, all of them are being at least 2. Can we then expect that all large integers are the sum of an eighth and b and c power? Well, the heuristic would tell us that the answer should be yes, if the sum of the reciprocals of the three exponents exceeds 1. There is a bit of care with this yes here. For example, if you take a and b equal to 2, and c your favorite even integer, then the sum of the three summons is still a sum of 3 squares because c is now even. And of course, not all large integers n are the sum of 3 squares. But we can explain what happens there. This is basically a two-adic obstruction that comes into play. And if we adjust the question a little bit and restrict n to appropriate congruence conditions, then the answer should indeed be yes, if the sum of 1 over a plus 1 over b and plus 1 over c is bigger than 1. Interestingly, there are not so many options to do this. If we assume that a is the smallest and then comes b and then c is the last, then we only have a family. A and b are 2, so we have 2 squares and then an arbitrary power. Or a is 2, b is 3, and then c must be 3, 4, and 5, or 5 in order to question mark be valid. And all these ternary additive problems have been dealt with. We don't know that all large numbers are representable, but we know for a very long time that almost all integers are representable, and almost all means if I just count them up to capital N, when I have few solutions, when I have few exceptions. For the family with 2 squares in here, so x squared plus y squared plus a c power, and for the special case of a square and 2 cubes, this was already known to Davenport and Heilbronn in 2 papers in the 1930s. Roth added the case of square root cube and the 4th power, and Bob Vaughan the case of square root cube and the 5th power. And after that point, we are done, except that we hope to do this someday for all large n. But you can still ask for exceptional sets, and one got a good upper bound by saving a power of n. In the 90s, early 90s, I looked into this and got something like square root cancellation in a couple of cases. Now, what is a bracketed ternary additive problem? A bracketed ternary additive problem. I'm not the first person to look at questions of this type, but you can introduce integer parts in various ways into the free sums. My motivation to do this but several recent papers have dealt with questions of how many primes are being represented by an expression like this. We still have our favorite ternary additive problem with an A for B for the C power S before from the two families, if you like. And now we have real coefficients, and I denote them by lambda A, lambda B, lambda C. I know that's bad notation, but maybe it's intuitive. Yeah, if A is 2 and B is 2, as will frequently happen, when lambda A and lambda B are not necessarily the same number. And the toughest thing in print that I know is take A equal to 2, B equal to 3, and C equal to 4, so this funny problem does not arise. And we assume that maybe one of the ratios of the coefficients is irrational, then this represents infinitely many primes. If one looks at the paper, one finds that a lower bound for the primes is being found, but the authors don't mention it. And I've deliberately withdrawn the name of the author here because I think that's a pretty weak result. So we discuss here some harder problems that entertained me during the lockdowns. So the first theme I would like to address, let's just choose what these other guys have done. But one can introduce brackets in a more ambitious way, and experts would realize if I have more brackets, then maybe this problem becomes harder. So why not introducing 3 brackets? That's part 2. But you can also do this in a different way, and I see an arrow at the blackboard that I can't quite correct right now. Of course, the B power here should be moved outside to be consistent with the first term, and the C power should also be moved outside to be consistent with the first term. So the exponents are outside the brackets. So on the questions that I now have, can I prove, as for the classical ternary additive problems, that these expressions here under the conditions that the numbers are real and ideally maybe positive numbers with one of the ratios being irrational, can I prove that they represent almost all integers? And is the exception of set so small that I can deduce that they even represent almost all primes? Because then I don't have to bother about this funny question about counting how many primes there are, roughly as many as we have primes. The toughest case in this problem is, as we have learned from the varying problem type, the last one that was actually confirmed was a square cube and the 5th power. That was the Vaughan paper from the 1980s. But similar results hold for all the other cases. So here is my first suggestion. And here I have 3 maybe positive, non-zero real numbers, 1 ratio irrational, and I'm counting numbers n up to n, but cannot be written, that was the first of these bracketed terms, or that cannot be written in the second form, where the exponents are inside the brackets. Then what I can prove is, but for both of these cases, we have very few exceptions. And it's typical if one wants quantitative versions of this, when one has to make an assumption about the algebraic nature of the quotients, lambda 2 divided by lambda 3 or something like that. Or one has to be content with a sequence tending to infinity where you can make big savings. And that happens, and I get square root cancellation as in the classical case. In particular, we see that the expressions 4 and 5 represent infinitely many primes. And if we restrict the prime count to the sequence n nu tending to infinity, then I have almost as many numbers being representable like this as there are primes. among the primes. So I'm not the first person to look at bracketed versions of classical additive problems, but I would like to present a new approach. So if I want to solve the first form of a problem, or the second form with three brackets, but the exponent still inside, then I propose to consider the following. Rather than looking at the problem of this type, I'm just counting solutions in X, Y, and Z, where this expression is in the interval between n plus 3/4 up to n plus 1. If I would now take integer parts, then the condition 6 alone guarantees that I have the integer part being equal to n. If in addition, I add new conditions, namely that lambda 3 times y cubed, the second term here, is near an integer in the sense that the fractional part is between 0 and 1/4. And I do the same for the fifth power, so it's my condition 7. Then I say that if I take integer parts for the y and for the z term, I'm losing at most 1/2, and therefore I will be between n plus 1/4 up to n plus 1 with this expression here. So now I can take integer parts inside again, but these are already integers, so that means I'm taking integer parts of lambda 2x squared, and the whole thing becomes equal to n. So all I need to show if I want to get exceptional sets, just count the number f of m of integers up to n, where the system 6 and 7 has no solution. If a system 6 and 7 has no solution, so then I'm bad either for that problem or for that problem. And now the proposition is that this is good enough for the problem to be solved. Let us have a brief look how this goes. And here is what is new in the approach that comes. The old school has applied the hardy little problem method directly. And then I end up with wild sums that have a bracket in the exponent. Well, that's a little bit messy because the e to the 2 pi I is a function of period 1. So I have to expand alpha times the integer part function here into a Fourier series. And that occurs inside E. It's doable, but it has the disadvantage that I can no longer use mean values of Hoover's lemma type. So if I do the transition to these conditions 6 and 7, let me just go back, but with the conditions 6 and 7, that's just inequalities. That allows me to work with ordinary wild sums. And that is, I think, a big advantage technically. And once that's being achieved, you can basically run a variant of a hardy little method smoothly and recover all what you have known for the classical additive problems. So we now encounter only the classical wild sums like this. And what I want to do, well, I'm just counting the n's between n and 2n for technical reasons. I have a function epsilon that looks like a lambda. That's just 1 minus 8 times the modulus of alpha, truncated at 0 from below. That has a neat Fourier transform. That's a function, a rescaled function of a type sine x over x being squared. So now taking Fourier transforms, we see, but the solutions of 6 are being counted with a non-negative weight, 6. Let me go back to you, that is 6. And, you know, I center things at 7 over 8 and go 1/8 to the left and 1/8 to the right. And the Fourier transform sees exactly the solutions with weights. They're not negative, so we are fine. So we want to show that this integral is large if we're only interested in solutions of 6. But there were also solutions of 7 simultaneously. So that's again an interval condition. This time I have a cube and a linear variable, and a 5th power and a linear variable, and again an interval of width 1/4. So let's do the same thing again. So if I want that, then for the linear variables, I take a Dirichlet kernel, but I smooth it out with the parameter r. So that's good, because now h of alpha roughly is almost 0 outside an interval where the fractional part is 1/2n. Almost 0. That's decaying to 0 very fast as n tends to infinity. So now I have to use a triple integral. One of the integrations is the integral you've seen before. And the other 2 integrals, with this h function in, and again the same kernels, take care of the other 2 Diophantine inequalities. So this integral r of n counts for simultaneous solutions of 6 and 7 with non-negative weights. So now I'm oversimplifying things a bit for a second. The decay of the function capital H allows us to roughly think of the variables that occur with capital H to be in their fractional part to be no bigger than 1/n, roughly. But K also decays very fast. So we can really think of beta 3 and beta 5 and alpha as being very small. Again, roughly something like 1/n. If that's true, then the moral is that we are reduced to the situation where beta 3 and beta 5 are very small. But then by Taylor expansion, the classical wide sums Fk that occur here, they have a property that this beta k doesn't actually change Fk very much. So in that sense, the beta k integrals drop out. So roughly speaking, up to constants, r of n will be just the integral that we have already seen one-dimensionally. But if you see an integral like this, and you've ever worked with Diophantine inequalities, you will immediately know that counting the solutions of 6 is roughly as difficult as the original equation. There is some Diophantine approximation argument, but that you can basically quote from the literature. And you will go home. Fine. Well, there's some variants, but I don't have time to actually discuss. It's actually easier than in the arithmetic situation of Waring's problem to show that almost always one even has an asymptotic formula for the number of solutions in the first problem, and probably even in the second. I was too lazy to work that out. And you can count the primes exactly if you don't treat them by the exceptional sets, and you get the proper and correct answer. You have an asymptotic formula that improves on all the previous work with respect. I have a 5th power here, and I have an asymptotic formula. That's all fine. But what about the third problem? This time I haven't made a mistake, so all the exponents are outside, fortunately. Can I also deal with this problem? Well, I can again translate by the tricks about the use of fractional parts. What I'm actually doing is I just look for the numbers k2, the integer that is closest to lambda 2 times x. That's what sits inside here. And I do the same thing for the other 2 entries. Then I have 3 inequalities for the case, and the sum of a square and the cube the 5th power of a case with a correct index corresponds to this equation here. So we have to solve 8 and 9 simultaneously. The fine print is a little bit different because now we have one Diophantine equation and 3 Diophantine inequalities to deal with, but morally, it is still of the same degree of difficulty. There's just one extra Diophantine inequality to deal with. But note that we have done something which is a bit dual to what we've done before. The original variables x, y, and z are now in the role of the auxiliary variables k in the previous thing. But the main equation now comes from what was previously the auxiliary parameter. But if you do the proper Fourier analysis on r cubed times r modulo z, roughly as before, then you get similar conclusions to both in theorem 1. Well, that's it. You can generate your favorite bracketed problem. And if a similar looking problem has been dealt with in a classical context of polynomials, then this method that I've just described will almost surely solve your question you might have about such bracketed expressions. I did all this when I got bored during the lockdown sessions, and I'm not sure whether I will ever write this up. Thank you very much.
Thank you.